Imagine you're standing on the deck of a cargo ship in rough seas. The waves are big, but nothing the crew hasn't seen before. And then the horizon disappears. Out of the dark, a single wall of water rises in front of you. Not a rolling swell, not a normal wave, a moving cliff. It hits the ship like concrete, snaps steel, and then it's gone. No second wave, no pattern, just impact and silence. For centuries, sailors have told stories like this, not just of big storms, but of impossible waves that come out of nowhere, move against the wind, and vanish as quickly as they appear. They were called freak waves, episodic waves, and for a long time, scientists had a simpler name for them: lies. All our neat equations said these monsters couldn't exist. They were dismissed as the exhausted hallucinations of sailors, the modern version of sea serpents and mermaids. And then, on New Year's Day, 1995, in the middle of a raging storm in the North Sea, an oil rig pointed a laser straight down at the ocean and recorded the impossible. It measured a single, towering wave that should not have been there. The legend was real. In this video, we're going to untangle one of the strangest mysteries in ocean science: rogue waves, how they form, why they were ignored for so long, and what they tell us about how little control we really have at sea. Long before we had lasers and sensors, all we had was stories. And these weren't just drunk tales from the local tavern. These reports came from some of the most credible navigators in history. Take Ernest Shackleton. In 1916, he was navigating the Drake Passage, one of the most dangerous stretches of ocean on Earth. In his diary, he describes one moment that froze him. He thought he saw a break in the clouds. Then he realized it wasn't the sky clearing at all. It was the white crest of an enormous wave. Their tiny boat was lifted and hurled forward like a cork in breaking surf into what he called a chaos of tortured water. The boat somehow survived. Shackleton did too. But the wave stayed in his notes as a warning. The ocean could throw something at you that didn't fit the rulebook. Go back even further, to 1826. French naval officer and scientist Jules Dumont d'Urville was sailing in the Indian Ocean when he reported waves more than 30 meters, over 100 feet, high. 3 of his crewmates backed him up. On paper, he was exactly the kind of observer science should trust: trained, disciplined, and careful. Instead, his report was laughed off. Critics called it an exaggeration. The verdict was simple: he must have been mistaken. But while the experts argued in lecture halls, ships were disappearing. The most famous was the SS Waratah, often called Australia's Titanic. In 1909, this massive 500-foot liner vanished off the coast of South Africa. No distress call, no wreckage, just 211 people gone in an instant. Official explanations focused on design flaws or hidden damage. Unofficially, among sailors, another idea kept coming up. The Waratah might have been hit by a single, overwhelming wave and rolled over before anyone could react. For the people who worked at sea, these impossible waves were part of lived experience. For most scientists on land, they were just that, impossible. The reason for this dismissal wasn't ignorance, it was physics. For over a century, oceanographers relied on a model called linear wave theory. In this picture of the ocean, the sea is made up of thousands of small waves that all pass through each other and add up, but don't really interact in a complicated way. Think of it like this. The model assumed waves were solitary travelers. They didn't talk to each other, they just passed by. If one wave met another, their energy simply added up. 1 plus 1 equals 2, and then they separated again. If you measure those waves over time, their heights line up into something close to a bell curve, a Gaussian distribution. In this kind of Gaussian sea, the ocean is predictable. Most waves are average. A few are big. But to get a true monster, a wave 3 times the size of its neighbors, you'd need dozens of waves to line up perfectly at the exact same moment. According to this math, a 30-meter, 100-foot wave should be a once-in-10,000 years event in a given patch of ocean. So when sailors kept reporting waves like that, the conclusion on land was simple. The statistics said it couldn't be true, so the sailors must be wrong. But the ocean doesn't care about our math. In the 20th century, large steel ships meant more crews actually survived encounters with these waves, and their reports were harder to brush off. Then came the case of the MS München. Launched in 1972, she was a German cargo giant, 260 meters long, modern, and considered extremely safe. But in December 1978, in the middle of a fierce Atlantic storm, she sent out a garbled distress call and then vanished. The search that followed found almost nothing. Months later, one of her lifeboats was recovered. It had been stored about 20 meters, 65 feet, above the waterline. The damage showed it hadn't been lowered in an emergency. It had been torn away by a massive force that bent its solid steel mountings backwards. Investigators concluded that the München had likely been struck by a very steep, almost vertical wall of water, a wave far larger and more violent than the ship was ever designed to survive. It was one of the clearest physical clues that the ocean might be producing waves well outside what the standard models allowed. But to finally convince everyone, scientists would need something more than wreckage and survivor stories. They needed to catch one of these waves in the act. On New Year's Day 1995, in the Norwegian sector of the North Sea, the Draupner oil platform was being battered by a severe storm. The platform was a fortress of steel, built to withstand the brutal conditions of the North Sea. The engineers calculated that a 64-foot wave was a once-in-10,000 years event. The platform was designed to survive that limit, and crucially, it had a secret weapon, a downward-pointing laser sensor, recording the height of every single wave that passed beneath it. At the time, the large waves were rolling in at about 39 feet, or 12 meters. Big, but nothing the platform wasn't built to handle. At 3:20 p.m., that laser recorded something that shouldn't have been there. Out of that already rough sea, a single wave rose up. From trough to crest, it measured 84 feet, or 25.6 meters, more than twice the height of the surrounding waves, and much steeper. This was the first clear, instrument-recorded proof of a rogue wave. The Draupner Wave, as it came to be known, was a revolution. It showed that the sailors' legends were real, and that the linear models of ocean waves were fundamentally incomplete. The data was undeniable. Scientists could no longer dismiss the stories. They had to explain them. The incident forced the entire maritime industry, from shipbuilders to insurers, to re-evaluate what the ocean is capable of. The monster was real, and we finally had its fingerprint. The Draupner Wave forced a complete rethink of wave physics. Scientists now understand that rogue waves are not just a matter of simple probability. They are the result of several complex, non-linear processes that can cause waves to behave in strange and unpredictable ways. The first and most common mechanism is constructive interference. Imagine the ocean as a chaotic dance floor of countless wave systems, all moving at different speeds and in different directions. Most of the time, they cancel each other out, but now and then, by pure chance, several large waves line up at almost the same place and time. Their crests stack on top of each other, their energies add up, and for a brief moment, you get one giant peak. It's like several people pushing a swing at exactly the right instant. Each small push adds up to one huge arc. In the ocean, that huge arc is a rogue wave. The second mechanism is wave-current interaction. This is particularly common in places like the infamous Agulhas Current off the coast of South Africa. Here, you have a powerful current flowing in one direction, while big storm waves, born thousands of kilometers away in the roaring 40s, travel in the opposite direction. Think of it like a traffic jam on a liquid highway. The current causes the waves to slow down, shorten in length, and pile up on top of each other, focusing their energy and dramatically increasing their height. This mechanism is one of the most reliable producers of rogue waves on the planet. The final and perhaps most mysterious mechanism is nonlinear focusing. This is where the ocean stops behaving like a simple sum of small waves and starts acting more like a system with feedback. Under the right conditions, a slightly larger wave can start to draw energy from nearby, smaller waves. As it grows, it steals more and more, becoming a single, unstable giant that stands out sharply from the sea around it. You can think of it as a kind of energy thief wave. It doesn't just happen by random alignment, it grows at the expense of its neighbors. In physics, these self-reinforcing waves are sometimes compared to solitons, waves that can hold their shape over long distances instead of quickly spreading out. This kind of behavior is so counterintuitive that it took controlled lab experiments, including a famous 2012 wave tank test with a model Lego pirate ship, to convince many researchers that nonlinear focusing could really create rogue waves in conditions that looked from the surface almost ordinary. Together, these three mechanisms, random alignment, hostile currents, and nonlinear focusing, explain how the ocean can occasionally break its own rules and throw a single, devastating wall of water at anything in its path. So we know they are real, and we have theories on how they form. But what makes a rogue wave so uniquely destructive? It's not just its height, it's its shape. Normal storm waves are sinusoidal. They have gently sloping fronts. A rogue wave is a near vertical wall of water, a phenomenon sailors call the hole in the sea. A ship doesn't ride up a rogue wave, it runs into it. The force exerted by such a wave is almost unimaginable. A normal 10-foot wave exerts a pressure of about 4 pounds per square inch. A large 40-foot storm wave can exert a pressure of about 17 pounds per square inch. A 100-foot rogue wave can exert a pressure of up to 140 pounds per square inch. That's over 20,000 pounds of force per square foot. No ship is designed to withstand that kind of pressure. At this point, steel starts to behave less like armor and more like tin foil. In 1995, the same year as the Draupner Wave, the ocean liner Queen Elizabeth II was hit by a 95-foot rogue wave during a hurricane in the North Atlantic. The captain described it as a great wall of water that looked as if we were going into the white cliffs of Dover. In 2010, the cruise ship Louis Majesty was hit by 3 successive rogue waves in the Mediterranean, which shattered the windows on its bridge and killed 2 passengers. Perhaps the most absurd example of their power is the Great Lego Spill of 1997. A container ship, the Tokyo Express, was hit by a rogue wave off the coast of England that caused it to tilt 60 degrees to one side and then 40 degrees to the other, flinging 62 containers into the sea. One of those containers was filled with nearly 5 million pieces of Lego, many of them, ironically, sea-themed. To this day, beachcombers still find these plastic treasures washing up on the shores of Cornwall. While rogue waves can theoretically appear anywhere, there are certain parts of the world where the conditions are perfect for their formation. These are the planet's rogue wave hotspots. The Agulhas Current off South Africa is one. The powerful Gulf Stream off the east coast of the United States, especially where it collides with storms, is another, a fact that may help explain some of the legendary disappearances in the Bermuda Triangle. The notoriously violent North Sea and the stormy waters around Cape Horn are also prime hunting grounds. But one of the most extreme rogue waves ever recorded appeared in a place that surprised everyone, off the coast of British Columbia, Canada. In November 2020, a lone sensor buoy recorded what has been dubbed the Untangled Wave. In absolute terms, it wasn't the tallest. It was about 58 feet, or 17.6 meters. But what made it terrifying was the ratio. Most rogue waves, like Draupner, are roughly double the size of the waves around them. The Untangled Wave was 3 times the size of its neighbors. It was a freakishly steep needle of water rising out of a moderate sea. In relative terms, it was one of the most extreme rogue waves ever measured. It proved that the most dangerous rogue waves are not necessarily the tallest, but the most disproportionate to their surroundings. For decades, we relied on luck to find these waves. Today, we have satellites. Using radar technology, the European Space Agency and NASA scan the oceans almost continuously, and the results are chilling. In one 3-week period, a project called MaxWave detected more than 10 individual rogue waves around the globe, each over 82 feet or 25 meters tall. The sailors' legends were not exaggerated. If anything, they were an underestimate. Rogue waves are not a once-in-a-millennium event. They are a common, if terrifying, feature of our planet's oceans. So, where does that leave us? The sailors' tales, once dismissed as folklore, have been vindicated. The lasers, the buoys, and the satellites all tell the same story. The monsters are real. Now we are trying to do something even more ambitious: predict them. Researchers are currently training artificial intelligence on decades of ocean data. They are teaching neural networks to spot the subtle, invisible patterns that form minutes before a rogue wave strikes. Early models are already showing success. They can offer a warning of just 2 or 3 minutes. It doesn't sound like much, but for a captain, that is the difference between life and death. It's just enough time to turn the ship's bow into the wave and ride it out, rather than taking it broadside. But we are still learning. Out in the vast, empty reaches of the open ocean, the data is scarce and the storms are wild. Predicting a single freak wave remains one of the hardest problems in science. And that brings us to the most important lesson of all: humility. For centuries, we trusted our equations more than the people who lived the experience. It took shattered ships, bent steel, and one impossible spike on a laser graph to force us to listen. The ocean wasn't breaking the laws of physics. We just didn't understand the laws yet. Even in an age of AI and supercomputers, the ocean keeps its secrets. And sometimes, the path to new science doesn't start with a complex theory. It starts with an old story that simply refuses to go away. So, I want to hear from you. Which of these theories scares you the most? Is it the traffic jam caused by currents, or the energy vampire waves that steal power from their neighbors? Let me know in the comments below. And if you want to untangle more of the hidden forces shaping our world, hit subscribe to World Untangled and join me for the next deep dive.